Hi everyone. State the monotone convergence theorem. A sequence of real numbers. Let's say, so a sequence is a map from the natural numbers into the reals. It's picking out infinitely many real numbers that we call the a sub n's. The a sub n's are real numbers. You have one for every natural number, and there's infinitely many of these. A sequence of real numbers that is bounded and monotone must converge. Okay, and this is only true for the real numbers, not the rational numbers. Okay, so proof. We will prove the case where we have monotone increasing rather than monotone decreasing, because the two proofs are very similar. We'll prove the case of monotone increasing, which means that the next one has got to be bigger than or equal to the previous. Okay. So let a sub n be monotone and monotone increasing and bounded. Okay, this is the assumptions. I'm setting it up. I'm saying, what am I assuming? We will prove that the sequence a sub n is Cauchy. Okay, because the real numbers are just basically defined as all the numbers that we need to fill in to the rational numbers so that Cauchy sequences converge. Just by definition, the reals are a set of numbers where every Cauchy sequence converges. Okay, so I explained that this is the end of the proof. So then we'll be done. If we can prove that a sub n is Cauchy, then it must converge, just by definition of a real number system. Okay. Okay, so how do we prove Cauchy? What is Cauchy? I'm helping the reader remember what's Cauchy. Well, I'll just put it in, maybe I'll put it in a thought bubble. For all d, there exists an n, such that any pair past that cutoff value implies that well, I was going to say zn, but I called it a, that these two are less than d. Okay, that's Cauchy. Okay, so that's what we need to prove. Okay, so here's the picture. So I'll draw the picture first. Here will be some upper bound. Here's maybe a1, then a2 is somewhere. Maybe a3 is also that same point, then a4, and etc. And it just kind of marches upward, monotone, increasing our sequence. But then it's bounded. And bounded implies there exists an upper bound. Let's call it U for upper bound. Okay. Now, we need to prove Cauchy. So we need to prove for all d there exists an n. That means we need to choose any d and then we have to produce the capital N. So choose some / any d in the positive real numbers. March backwards, march left from u. So we're going to go d, and if if u minus d is not is not an upper bound, then we're sort of done already. So remember, u is an upper bound. That means all the a sub n's, wherever they are as they're marching, are less than or equal to u. Now, if we march back to u minus d, and this is not an upper bound, that means there exists some a sub capital N. Maybe it's a 205 that that makes u fail to be an upper bound. Okay, so if u minus d is not an upper bound, then there exists an n such that a sub n is greater than u. Because it's not an upper bound, then it has to fail at some sequence value. But then all the rest of the sequence values are bigger than that and less than u, and we'll be done. So hold on, but I have to say that more carefully. If u minus d is not an upper bound, then there's something that shows it's not an upper bound. Else, if u minus 2d, if I step back twice by d, is not an upper bound. And else here means like, well, then if u minus d is an upper bound, then we check u minus 2d. Else, if u minus 2d is not an upper bound, there exists an n such that a sub n is greater than u minus 2d, showing that u minus 2d is not an upper bound, etc. At some point, at some u minus kd, or maybe I'll just say, since u minus kd is eventually, k being some integer, like some number of steps going to the left, is eventually less than a1, there is some u minus kd which fails to be an upper bound. Okay, and here I'll tell the reader, by the way, k is some positive integer, right? These are the steps: u minus 1d, u minus 2d, u minus 3d's, etc. And so at some point, we're going to get past a1, and then that's clearly not an upper bound, because a1 is greater than u minus kd. But okay, so there is some u minus kd which fails to be an upper bound, so that, but I have to say, but u minus one less step, like the previous step, is still an upper bound. Okay, and now I'll just draw another picture. Here's the u, here's d, d, and let's say it was here. So here's a1, a2, a3, and here's the, this one is an upper bound. This one fails to be upper bound. Well, that means that then there exists an n such that a sub little n is between u minus kd and u minus 1 less. Since u minus k minus 1d is an upper bound, is still an upper bound, I want to say that all the a sub n's now are in this little range of D. And since a sub m, or maybe I'll just say a sub capital N plus n is always greater than or equal to a sub capital N, then all the rest of the a sub n's of the a sub n are within D of each other. In other words, they're in here. Oops, that was too big. They're here. They're in here. Because this fails to be an upper bound, so there is something in here. But then it's monotone increase, so everything else past that has to be greater than. But this was still an upper bound, so it can't be over here. So they all have to be here. This means that anything past that capital N that must exist, because this u minus kd failed to be an upper bound, so there's something past it. This means mn past that implies an minus am less than d. The proof is over. We showed it's Cauchy, so that's it. Let's review what we did. We chose the case monotone increasing and bounded, and we proved Cauchy. If we can prove Cauchy, then it must converge because it's a real number sequence. And the reals have Cauchy sequences always converge. So we needed to pick some random D, so any D. We did it here. And we started marching left from the upper bound that we know exists. And, if u minus 1d, u minus 2d, eventually there's something that is not an upper bound, but the previous one is an upper bound. And that means that everything will be trapped inside this little interval of step length d. But if everything is trapped there after a certain cutoff, this a sub capital N, that demonstrates the failure of this line to be an upper bound, well, then we're done. We have that everything else is bigger than a sub capital N, but smaller than this last upper bound. And so it's within D of each other. That's it. Okay, that was a recap.